as I was preparing for this to give this presentation, I was also this weekend reading my copy of the New Yorker magazine, and in it there's this really an interesting article which talks about artificial intelligence, which is being developed for use to replace fighter pilots. So the lead of this story was, or the focus was on a DARPA competition where they're testing various approaches to artificial intelligence within actually flight simulators to see if they can shoot down adversaries, including in dogfights, including shoot down the best real pilots who are sitting also in those simulators. And so it was an article that actually related to the subject of this talk to some degree in the following sense. First of all, the way these artificial fighter pilots are going to work, of course, is by being able to predict what happens physically to an aircraft as it's being navigated through space. So we have to be able to run a physical simulation of something that occurs in real life. And so you can imagine, in whatever form of machine or deep learning these artificial intelligent programs are running, numerical mathematical routines are going to be used very heavily. And so for sure, on a topic that is as important as this, we don't want our routines to be limited by classical limitations of depth and speed. So quantum computing may also play a role in something as far from standard scientific work as this. A second thing that was highlighted by this work is this concept that you can gain trust slowly, but you can lose it very quickly. So they were testing, to what extent real fighter pilots would be willing to let an artificial intelligence program take over the airplane, and how reticent they were to do so. And this also reminded me of the current hype around quantum computing, where we are all of us making pretty strong claims about the future, but we're sort of riding this very precipitous hype wave, and we have to be careful always not to overpromise, just noting how quickly the trust that society has placed in us can fall apart. And then the third thing that this really illustrated was, well, there is really a lot of application of numerical mathematical computation in the real world that would be hastened by the development of a quantum computer. And a lot of people are counting on us to do this right. So we really better make one happen. So fortunately, I read this article early enough that I could hop on to Amazon, and they could quickly deliver a product to my doorstep. So I placed an order for some quantum technology, just to see if I could go ahead and perform these computations. So this arrived on my doorstep within a day or two. I was quite excited to receive it, and I popped it open, and here's what I found inside. So I was really quite disappointed that this is what they were selling to me as quantum technology on Amazon. But then I took a little closer look at the contents of this box. I used a high resolution microscope, and I put in some laser light of a particular color. And lo and behold, I found that this box actually contained very many qubits, all of them entirely perfectly calibrated, perfectly identical, the same as one another. They each would possess very long-lived quantum coherence, and they can in fact be the basis of the quantum technologies that may even be used in such an advanced application as what I started with. So that's going to be the gist of my talk: is that atoms are not the thing about the fighter pilots, but that atoms are potentially a great resource for quantum information science quite in general. So the physics of ultra-cold atoms finds its roots in atomic physics work that was established experimentally over much of the 20th century. That's sort of the roots. And then the trunk of this tree was built from advances that allowed us to control not only the internal state space of neutral atoms, single atoms, but also to control their motional state space, to place them in very specific locations under very favorable conditions for experimental work. And from that, we've then developed as a sort of a very fruitfully branching tree. We've developed applications of ultra-cold atoms in a really wide range of scientific pursuits. There's research on ultra-cold atoms, which treats them as a new kind of material and explores concept in condensed matter physics. There's applications of ultra-cold atoms for sensing, because the atoms are perfectly identical, perfectly calibrated with um, their response to outside stimuli actually being determined by fundamental constants. So certainly a reliable sensor for many applications. There's been some really gorgeous work on the precise mathematics and realizing some long-standing predictions about few body systems, which have been established experimentally through cold atom research or been verified. There's been a lot of application of ultra cold atoms, not just to study materials, but to study materials that are driven into regimes where real materials could never exist. So we can study far from equilibrium quantum dynamics. And then, of course, maybe most relevant to this workshop, but really a derivative of all this previous work, is the application of cold atoms as a quantum computer. So in my talk, I'll highlight some works largely coming out of my lab that talk about some of these applications of ultra-cold atoms for the broader pursuit of quantum information science in the area of quantum simulation, quantum sensing, and then finally offering some perspective on where we stand vis-a-vis quantum computing. Let me start with the first topic, which is a topic in quantum simulation, where we find experimentally a new way to look at the band structure of materials. So quantum simulation is an attempt to understand real physical systems by representing them in other physical systems. And rather than bang your head against the real physical system and try to extract experimental data from it, which may be a complicated thing to do, you instead play with your alternate representation of your quantum system. You perform experiments on it, and the results of those experiments are now statements about what does a particular model for physics predict as its outcome. So here we're interested in quantum simulation of materials, and in particular, we're looking at the fact that many of the properties of materials are determined not just by band structure, but specifically by certain singularities that occur where two bands touch each other at some singular point. So the famous examples in condensed matter physics where this occurs is graphene as a two-dimensional system, or other now three-dimensional systems that possess these singular points in band structure. And when the Fermi energy of these materials lies near those band touchings, all sorts of interesting physics ensues. In terms of graphene, the way to model the physics of graphene is to create some physical system under your experimental control, which has the same lattice structure, in this case, the honeycomb lattice, and to study the effects of band structure in that system. In my lab, we do this experimentally. We take a gas of rubidium atoms at very cold temperatures, and we put them into a lattice structure which exactly resembles the lattice structure of graphene. So in particular, we take laser light that focuses on these atoms from several different directions. And in the overlap of these laser beams, we see optical intensity patterns that create a potential in space which resembles the potential that electrons see when they move through graphene. So I'll focus just on this middle picture, which is what we obtain in our lab when we have three beams at this particular wavelength, 1064 nanometers, that overlap physically in space at the location where the atoms are positioned. And this light field has intensity maxima at the locations of a honeycomb lattice, as shown here. And atoms at this, rubidium atoms experience light of this particular wavelength are attracted to the points of maximum intensity. And so they inhabit a lattice structure, which is basically the graphene lattice structure, where now The spacing between lattice sites isn't on the order of an angstrom, but it's on the order of 400 nanometers. But nevertheless, we hope that the motion of very cold atoms inside of this potential landscape gives us some clues as to the motion of electrons within something like graphene. Our system also allows us to have this optical lattice not just be stationary in space, but also move in space. So the potential is produced by the interference of 3 laser beams. And if I vary the phases of these laser beams or their frequencies, then this optical lattice will physically move in space. And that's a very handy facility for us, because it allows us to take atoms and place them, it turns out, arbitrarily within the band structure of this lattice, of this material. So let me show you how that's done. So let's say we have an optical lattice, and we place atoms into this lattice. We slowly turn on the lattice while the atoms are there, and the atoms settle into the lowest energy state in this optical lattice. That happens to be at 0 wave vector, so the non-moving initial state, and in the lowest band. But now imagine that we accelerate the lattice. So we tweak some of the frequencies on the laser beams, and now slowly the lattice is made to be moving away at some finite velocity in the lab frame. As far as the atoms are concerned, this ends up promoting them to a velocity within the lattice, which is minus the velocity of the lattice in the lab frame. So as such, we can promote our atoms from the center of band structure at the gamma point at Q equals 0 out to somewhere else in band structure and have the atoms acquire that block state at that location, and we can probe it. Alternately, what we can do is we can first accelerate the lattice, let's say at a low intensity of laser light, and then we can gradually load the atoms into a moving lattice. And this ability turns out to also allow us to take atoms and place them into excited bands of the band structure. They can be adiabatically mapped just into the ground, not just into the ground band, but into any band of the band structure. And that allows us really to place the atoms at all places within band structure, including in the high excited states. Okay, but our interest in this particular quantum simulation is to characterize very well the band structure at these touching points, known as Dirac points in the structure of a graphene. So this is the point where the lowest band, the first band, and the next excited band, the second band of graphene, end up having a touching point. They end up being degenerate with each other right at this location within band structure, known as the K point in the Brillouin zone. To understand how the energy of these states and also the nature of these states varies with a wave vector, it's useful to adopt a pseudo-spin language where you imagine a particle, either an electron or in our case, a neutral atom, that is trapped at the A site of the lattice. We'll call that spin up. And an atom that's trapped at the B site of the unit cell, we'll call it spin down. And then it turns out that the block states or the band states away from the Dirac point can be described as pseudo-spin states where the atom or the particle sees some equivalent of a magnetic field which points always away from the location of the Dirac point. So for example, at this location over here, the higher band and the lower band, they would just be described as spin X and spin minus X states and so forth. And this model, it tells us what is the energy variation at the Dirac point, and also what is the state geometry at this Dirac point. So how do we characterize this geometry? And you notice that this geometry is also obviously singular because I can't, from a knowledge of the band structure near the Dirac point, I can't make a unique assignment of states at the Dirac point. So how can we characterize this sort of singularity that occurs in the geometry of the system? The first attempt to do so is to measure a Berry phase, which you do by studying, as you know, the holonomy. You take a state and you wrap it around a closed loop in parameter space, and you see whether the state has been modified owing to that parallel transport. And doing this experimentally is as follows. You take a gas of atoms, you or this was done in the block group, where they prepare a gas of atoms at this point of band structure. They place the atoms in a superposition of two internal states. They drag the atoms on a path that encircles the Dirac point, and then they measure the interference phase between these two populations. And the interference phase measures a pi phase shift, which is the Berry phase that's acquired as you go around this singularity. In our experiment, we considered a different parallel transport probe of this band structure. We considered the following parallel transport. Say you take a gas of atoms that starts in a well-defined state somewhere in band structure, in this band structure, and then you translate the atoms, and remember, we know how to move atoms through quasi-momentum space by moving our lattice in time. So we can take the atoms and we can move them right at the Dirac point, and then have them hook a turn by some fixed angle and leave the Dirac point also along some ray. And this parallel transport, as you can see quite trivially, should lead to a transition between the bands. If we look at this should be a non-abelian non-holonomy, if you will. And what should occur in particular is that the population of atoms in the final states at this position in band structure should be divided between population in the lower band and the upper band according to these formulae. And basically what's happening is, imagine I start off over here with a gas that is in an eigenstate of the system. So let's say it's spin down. We move it toward the center. It always experiences a pseudomagnetic field pointing down. So it stays pointing in that way. We tune that magnetic field to 0 at the Dirac point. And then we turn that magnetic field slowly onwards, but pointing in the x direction, let's say. So now your system would be projected into equal superpositions of the plus and minus x states, and that would lead to this predicted distribution of population. So experimentally, we run exactly this experiment. We take atoms, we move them through band structure, we hook them over, we hook them by a turn by some angle, and we then measure the population in the final bands. I won't go through the great details of how that's done, but the outcome is basically to reproduce this cosine squared and sine squared dependence that was predicted by theory. So what does this quantum simulation teach you? To some degree, I would say not so much, because this is a result that, look, I could have derived for you in a few lines of Mathematica. But on the other hand, I think of this as an important starting point for studying more complex problems where we don't really know the answer. And secondly, and I think this is where the quantum simulations that have been done have the greatest impact, is that they allow theorists to dream. Now you can dream about different phenomena that might occur far out of equilibrium in these systems. Let me give you another example of what cold atoms are doing in the area of quantum information science. And this one falls into the area of quantum sensing. So we wanted to study a condensed matter, or I guess a thermodynamics problem. We wanted to study the thermodynamics of a mesoscopic system that undergoes some sort of non-equilibrium process. In particular, we chose to examine the process of evaporation, where atoms or particles in your coffee cup hop over a barrier and leave. Now, there's theoretical works that tell us what are the dynamics of evaporative cooling in terms of the average number of atoms that leave, the rate at which the substance left behind gets colder, and so forth. What hadn't been predicted by theory and what had not been visible yet in experiments is what are the stochastic fluctuations in this evaporated number. And stochastic fluctuations in thermodynamic systems, as you know from certainly in all mesoscopic systems, including biological ones, are prominent when you go to systems that are small. So as you look at mesoscopic rather than macroscopic systems, these fluctuations play an ever larger role. So we wanted to use high precision sensing to make measurements of these fluctuations. And in order to do so, we chose to make use of high finesse optical cavities and the phenomena of cavity quantum electrodynamics. Basically, we use just a simple prediction, which is that if I place atoms inside of the mode established by this cavity, then there will be a shift in the frequency of the cavity that is proportional to the number of atoms that I've placed in there. So I can just monitor the resonance frequency of this cavity in real time, and I can make very sensitive measurements, in fact, down to even single atoms, of the number of atoms that remain inside of this thermodynamic system. I won't go through this slide just for lack of time, but just to describe roughly how this is done, the cavity resonance frequency shifts as a function of time. It shifts to the right as atoms are lost from our system. And then using some feedback to keep our measurement always highly sensitive, we obtain a real-time measurement of the number of atoms that are inside of our cavity during this process. And we can run this experiment once and obtain a very precise real-time record, so a full temporal resolution record of the population of atoms during this particular evaporative process. And this is using just a tiny bit of light because we want our light not to be perturbing our atomic system too much. We want to measure the native variations of the system and not the stuff that's brought about by the active measurement. So you can imagine that by looking at one of these traces, we can gather a lot of information by trying to correlate, let's say, the measurement of the atom number we make at one time to the measurement of atom number we make at some later time.
Oh, hey, can I
Yeah,
interrupt real quick? Can I ask like
please.
why exactly like the frequency shifts upward as more atoms leave?
Yeah, sure. So in this, we're working at this point in a dispersive regime where each atom acts a little bit like a little bead of light. It shifts the phase of the light that goes through it by some slight amount. And it does so in a way that appears to make the cavity well, either shorter or longer to think about what that is. But basically, the light that passes through the gas acquires an extra phase shift upon passing through the gas. And now we have to tune the wavelength or frequency of our cavity so that also including the phase shift from this atom, we have a half integer number of wavelengths along the cavity to be on resonance. So that's the reason. It's the dispersive shift. Did that explain it? Okay, great, thank you. So we can acquire data not just from this one run of the experiment, but we can also actually run the experiment many hundreds of times and watch the same thermodynamic process happen over and over again. In doing so, we gain a lot of statistical information. So this data set is really quite rich. We can separate out variations that are caused by sort of trivial things like mistakes in experimental preparation from variations that happen because of some native dynamics of the system, which is the part that we're more interested in. And the most important outcome of this experiment so far was observing clearly the mesoscopic or the stochastic fluctuations that occur due to this non-equilibrium thermodynamic process. And this has, I think, future applications in studying quantum transport, things like quantum thermodynamics and heat engines, other types of non-equilibrium dynamics. So we're excited in pushing this application of quantum sensing forward. Now, what I've told you about so far is I've told you that one can place atoms in optical lattices. In fact, the sites of this optical lattice, if you were paying attention, have a spacing of a little less than a micron or so. And people know, both in our lab and in other labs, we know how to use atomic interactions to induce a change where each single one of these lattice sites will be occupied by just one atom. And that's a really nice starting point for quantum computing because you can think of this as a big array of qubits. I've also showed you just a little bit of applications of atoms inside of optical cavities. What I didn't really describe to you very much in depth is that there are potentially ways to have atoms that are both placed within the same optical cavity exchange photons with one another. And those photons can convey quantum information and lead to entanglement. So atoms in optical cavities are also being considered as the underlying approach to performing quantum computing. A third application, which has arisen most recently among these choices, is experiments where atoms are placed in optical tweezers. So different than these optical lattice configurations, here you place atoms in traps that are quite far from one another. But nevertheless, one can create arrays that are fairly perfectly filled with a single atom per optical tweezer, and that can now be the basis of your quantum computing technology. So this is how atoms are arrayed. Now the question is, in these different platforms, what kind of features would a quantum computer based on these approaches have? In the case of atoms in optical lattices, which is maybe one of the earlier entries into this into the field of maybe performing quantum computing with neutral atoms, but has nevertheless proceeded somewhat slowly, I would say. The way in which you're going to eventually place quantum gates between atoms is by making use of contact interactions. The fact that two atoms at the same lattice site can interact with one another, and can in particular do so in a way that depends on the internal spin state of the atom. So a downside of the contact interaction is that it's weak, and the gates therefore are going to be quite slow. So, if I'm looking to realize some, obscene number, 10 to the 16 or whatever gates in a quantum computer, and I have to take a millisecond to execute each one, that's going to be pretty painful. On the other hand, atoms in optical lattices, we've shown them to be quite coherent, and contact interactions are non-lossy and also very coherent. So there are some prospects still to be pursued in this platform. In the case of atoms in optical tweezer traps, the way in which interactions are introduced, as I'll say in a second, are by exciting atoms transiently up to Rydberg states. This has the advantage that the gates are very, very fast. The gates are still only short range, so still only nearby atoms are coupled to one another. And the coherence appears to be moderate for these gates. For atoms in optical cavities, the exchange of cavity photons can, in principle, give you very fast gates, and also can couple atoms at any location inside of the optical cavity. So to the extent that your entire computer lives inside of this cavity, you can consider the atoms to be all-to-all coupled. The downside is that the coherence of these gates is going to be quite low because of optical losses. So you can think about applications of these different technologies in different corners of the quantum computing space. So atoms in optical lattices, as I've suggested to you, are really great for quantum simulation because they represent condensed matter physics directly. In terms of quantum computing, I would say the highest prospects are to try to realize cluster states in these systems and use them for measurement-based quantum computing. As far as atoms in optical cavities are concerned, I would say that I think we should mostly think about quantum simulation of systems that are deliberately open as being a pretty interesting topic on their own, and using optical cavities because of the interaction with a measurement medium for the purpose of high fidelity, maybe fast measurement. And then atoms and optical tweezers, these are the ones that I think are moving at really high speed toward the realization of not just programmable quantum simulation, but also quantum computing. So it's a really exciting direction of the last 5 or so years. The way these tweezer experiments work is the following. You take a gas of cold atoms, which is already, as you imagine, quite a scientific feat. And then you place these trapped atoms into a number of tightly focused optical beams, laser beams. So here's a picture, but it's relayed into a vacuum cell. And now we have a bunch of tightly focused traps, each of which can gather some number of atoms. You then apply laser cooling light, and it turns out that that laser cooling light reduces the number of atoms inside of a tweezer to either 0 or 1, but you can't hold, there's a blockade that doesn't allow there to be more than 1 atom in the tweezer. So that's your starting point. So some of your sites have a qubit, some of your sites don't have a qubit. But fortunately, all the ones that have qubits, they fluoresce very brightly, as we can see in images taken also in my lab. And based on this image, you can figure out which tweezers hold qubits and which ones don't. And using that information, you can sort them. So here's an example of how you sort the atoms in one dimension. You find out that in this sequence of traps, there's 6 of them or something that hold single atoms. And then you basically reposition those atoms to make a fully filled, in this case, one-dimensional array. But more recently, people are also making rather interesting two-dimensional, and eventually I think people will think of three-dimensional structures for their quantum computers. Now you need to mediate interactions between the atoms. And the way this is done is by promoting atoms to high-lying atomic states known as Rydberg states. These Rydberg states have very large electric polarizability, and that makes them very sensitive to one another. So the dipole-dipole coupling between two Rydberg atoms is substantial even at a distance of several microns from one another. And that allows for a variety of types of interactions and quantum gates. You can make sort of controlled Z gates and other types of gates using the Rydberg blockade. And then finally, at the end of a computation, you read out the tweezers. And again, you read them out typically in experiments by imaging. And this approach to quantum simulation and quantum computing has already led to some of the most powerful quantum simulations and the beginnings of tests of quantum advantage, even in a technology that is only several years old. So it's really quite an exciting development. One thing I want to point to in this experimental sequence is that we do spend a lot of time looking. We have to take images to figure out which tweezers are full. And the imaging is kind of a slow step because you have to wait with a low efficiency microscope to collect a few photons and to see those few photons on top of a bright background. And then again, at the end, we have to collect information and measure. And the measurements that are performed at the end, not only are they slow, but they're also complete. So there's so much light scattering that occurs in one of these imaging events that all of the qubits are read out at once. So you can think of a number of improvements. You can think that would be nice to learn how to read out the state of tweezed atoms more rapidly. That would make your experiment run quicker. And also, quite importantly, it would be nice to be able to make an atom-specific measurement, just to measure the state of this qubit and not all the other qubits. Let them all, the other ones, remain coherent while we measure this one, for example, for the purpose of quantum error correction. So what we've been doing in my lab is learning how to do that step. And we do so by taking a tweezed atom and placing it inside of an optical cavity and using the optical cavity to quickly read out either by transmitting light through the cavity or by fluorescing light and having the atoms scatter light into the cavity, try to very rapidly and with high fidelity read out the state of a tweezed atom. So that's work that these folks have been doing. And our readout has 3 outcomes. We want to be able to distinguish between a tweezer that doesn't contain an atom, because maybe it was lost during a computation, or maybe when we get to the sorting stage, it simply was a tweezer that didn't hold an atom. Or we want to be able to measure where the atom is in spin up or spin down. In our case, spin up we'll consider to be the upper hyperfine level in rubidium, and spin down will be the lower hyperfine level. So one way we do this is by looking at fluorescence. We take a tweezed atom, we put it in a cavity, and we measure its fluorescence for 20 microseconds. If the atom is in the upper hyperfine level and there's an atom in there, it will scatter photons to our detector and will read a bright signal. Next, we repeat the same measurement, but we add repump light. Repump light takes an atom in the f=1 level, so the spin down state, and places it in the spin up state, and now it can cause fluorescence. And so you can see the 3 scenarios in our experiment. So if we have an atom that was in the f=2 state, we get a bright count both in the first and second period of fluorescence. If we had an atom that was originally in the spin down state, it turns out to be dark during the first period, but bright during the second period. And if we had a tweezer that had no atom in it, well, then it would never fluoresce into the cavity, and we can identify its data down here. And you see that the measurements are already, in our first attempts, turning out to be a pretty high fidelity. So we're able to make measurements of a single tweezed atom within about 40 microseconds, which is short compared to the time it usually takes to image an atom. And appealingly, it's even short compared to the lifetime of a Rydberg atom. So you can really measure with very high temporal resolution what's happening inside of your quantum computer. We've also made measurements where we measure the presence of an atom in the cavity through transmission. These measurements, I won't go through the details. Again, we can separate out the 3 different circumstances in our experiment, and we obtain also pretty high measurement fidelity. I think here we mostly were limited by some state preparation errors. But in any case, this is what we're going to build on, is the ability to measure the state of tweezed atoms quite rapidly. The last thing I want to tell you is to invite you to get involved in our the Challenge Institute for Quantum Computation, the CIQC, and maybe you know many of its members. Here's the members of the CIQC. As you know, we come from a lot of places, and I wanted to highlight 4 people in particular, because these are the people that organized this awesome IPAM conference that you're attending right now. So I really want to thank them for their efforts. We have a deep partnership between IPAM and the CIQC, and one of the first outcomes of that partnership is the workshop that you're attending. And I'm really happy that my colleagues kind of jumped on the opportunity to take some leadership and to pull together this community to meet. We're also planning for a long program on the connection between mathematics and quantum computing, which will take place in fall 23, I think. And what does the CIQC do? Well, it studies all these topics. You'll recognize our research foci are in the area of developing quantum algorithms, continuing the habit of trying to establish quantum advantage over classical computing systems, and then also to investigate, in particular experimentally, what goes wrong when you scale up quantum systems and how to make them perform well even when they're at large scale. And I show this slide because of this last boxed invitation. So it turns out that we have the means to appeal to the NSF for extra funding. For those outside of the Quantum Leap Challenge Institutes, ours and others, you can also talk to Andrew, for example, who spoke this morning. If you want to collaborate with us on an experimental topic, a theoretical topic, or some combination, please approach us with some ideas, so we can sort of carry those ideas to the NSF and try to get everybody happily funded together. They're really wanting to expand the roles of these QLCIs so that more researchers from who are not necessarily part of one of those centers can benefit from their existence. So we'd be happy to promote that. And with that, I'm roughly on time, so maybe I'll stop here. Thanks, everybody.